Hello and welcome to this short presentation on the Sonus PD for partial discharge detection. My name is Rudy Woodridge. I'm the Vice President of Engineering Services at IRISS Incorporated out of Bradenton, Florida. So what's partial discharge? Partial discharge is basically an electrical discharge that does not completely bridge the space between two conducting electrodes. Now that sounds kind of complicated, but what it really means is that it's like a spark plug, a spark gap that's taking place. A discharge of not all of the energy, but some of the energy, the potential electrical energy between two different voltage level components. Okay, so let's talk about this a bit more. Where does it happen? Well, it can happen in a few different ways. It can happen inside the gas-filled voids in solid insulating material. So this is cable insulation, standoff insulators, any insulating component of your medium and high voltage switchgear. You can have little defects, little voids that formed when they were forming the insulation, and that somehow did not come out during the curing process, and they remained there after the component was finalized in its manufacturing. And these act like little spark gaps inside the component, and voltages that are across that component from phase to phase or phase to ground can potentially cause partial discharges of energy to happen through those voids. Secondly, it can happen in the bubbles in liquid insulation. So we can have air and other gases that are circulating in the tank of an oil-filled transformer, for instance. And those can be, again, present with significant voltages between phase and ground, the tank itself, and you can get induced partial discharges that are occurring through those bubbles. And then lastly, you can have partial discharge that occurs in air. Now it's usually a discharge essentially from phase to phase, or again phase to ground, and it's happening partially because air is not a perfect insulating material. All right, air is a pretty good insulating material, but it's not perfect. So you can have partial discharges that occur just in air. Now let's talk a little bit more about what happens mechanically inside of an insulator. So here we have a cable, right? We have the high voltage conductor in the center of the cable, some sheathing material, some insulating material, and then an external earthing sheath on the outside. And we have this little defect in here, this little gas-filled void. Now, why does a partial discharge take place inside that void? Well, it's because the dielectric breakdown strength of air is so much lower than the polyethylene, LDPE material that makes up the actual insulating casing of the cable. So it doesn't take super high voltages for us to break over that withstand voltage and actually cause a partial discharge of energy to take place. And these tend to happen on the rising voltage waveform as you cross zero, and on the falling waveform after you've crossed zero. So, this is what's happening, is we have these little voids, and then we have a little sparking and a little arcing that's going inside the insulating material. And that has some long-term implications for that material's mechanical strength. What's happening inside there are three things. You have ionic bombardment that's taking place as a result of the electrons that are being released across the gap. We have a localized heating effect. And then thirdly, we have some chemical reactions that can be taking place. So the actual arcing can slowly eat away at the surrounding insulating material, making the gap internally larger, right? That defect gets bigger over time, but it also changes the surrounding material's chemical makeup because of the combined heat and electrical energy that's being discharged. Can have a breakdown effect chemically on the surrounding material. So it can slowly release gases, it can slowly carbonize, it can do all kinds of things depending on how it reacts in the presence of a little spark. So what's it mean? So we can see on the surface of components, we can sometimes see these evidences of surface tracking. right? We can see electrical treeing. We can see signs of arcing that occur on some equipment. And then we can see carbonization effects on equipment as well. So slowly over time, over extended periods of time, these defects will start to mechanically change the, the components that they're impacting. Where's it going to occur? Well, it occurs at a number of different places, at actual cable or junctions and terminations, bus bar connections, any spouts, any pointy places tend to cause corona. Corona is very dependent upon the mechanical structure of the equipment. And it's been estimated that up to 80% of switchgear, medium voltage switchgear related failures, medium and high voltage, are suspected to be starting out as a partial discharge event that eventually turns into a full-blown face-to-phase or face-to-ground fault. And we can have different types of partial discharge. There could be gas bubbles within a liquid insulating material. We could have voids within a solid insulation. We could have corona occurring around an electrode in gas, usually air. Or we could have surface tracking or arcing across the surface of an insulating material. Now, both arcing and tracking will make noise in the ultrasound spectrum, and we can use software to differentiate if it's actually an arcing event or a tracking event. They will have different characteristics in the time domain that can be differentiated and therefore identify which event is actually taking place. And what happens if this is left unchecked? Well, eventually it can cause in cables outright failure. So we have a loss of supply, an unplanned outage, customer interruption, lost customer minutes for utilities, and then we've got to go figure out, well, where did the actual failure occur? Because we've got, hundreds of meters or sometimes hundreds of kilometers of cabling, and we have to go find where the failure has actually taken place and then figure out, okay, how are we going to splice a new piece, or do we need to string all new cable? In switchgear, and this is mostly 5 kV and above applications, we can have full-on arc flash or arc fault type events that occur as a result. So over time, the insulating material is being worn away from the inside out, like a cancer almost, that it's eating away from the inside of the material over time, and eventually it loses its ability to be an insulator, and it allows a full-blown discharge of energy between phases or between phase and ground to occur, which will cause significant catastrophic and collateral damage to the surrounding components and surrounding equipment. So it's not just the component that started out with this little defect that is impacted. It can be a much larger instance of equipment that fails as a result. I recently talked to a mining operator who had a partial discharge event that was occurring inside of a potential transformer inside some medium voltage switchgear, and it failed. The actual potential transformer failed, but it failed so catastrophically that it took them out for a number of days while they were, getting replacement components and replacement switchgear in place so that they could get up and running. So this was on their primary incoming switchgear. It took out the entire facility. So you can imagine how quickly something like this can cascade into a much bigger problem. So where's it happening? As I mentioned, it can either happen phase to phase between different components, or it can happen between phase and ground. So either of those stresses can be taking place, and we need to be mindful of both of them. When we have these events, they typically happen either on the surface of the insulator, the surface material. All right, so you see it on standoff insulators, you see it on insulating boots, things like that, and that's the arcing, tracking, and corona. Now we can detect that because it gives off noise in the ultrasound spectrum. So we can use ultrasound listening devices and handheld devices to listen in for those surface events. The internal discharges, the ones that are happening inside of the insulating material, are much harder to detect. Well, why is that? Well, it's because while they will also generate noise in the ultrasound spectrum, All right, it is an arcing event that's going on inside there, but the energy that's being released, the sound energy, is relatively small, number one. And number two, it would have to travel through the insulating medium and then into the surrounding air. So it has to pass through multiple medium to get to a place where we could listen to it with a handheld ultrasound device. So the level of sound energy that would transmit through those multiple mediums would be significantly diminished from the original fault. And the original faults tend to have very, very low levels of sound energy generated in the first place. So airborne ultrasound as a mechanism to find these partial discharge events that are taking place inside of insulating materials is really not particularly practical. So we need a different methodology to do that. So again, we can have these things happening in joints and accessories, so standoff insulators, insulating boots, etc., where the void or defect is within that component, or it can be happening inside of actual cable insulation. So either of those two things are possible as where we'll see these internal PD events. So how do we go and detect that? Well, we use a special detection device that uses a capacitively coupled sensor. It's also sometimes called transient earth voltage detection or TEV detection. And the TEV sensor can be a permanently installed, or as shown here, can be a handheld device, which you touch it to the exterior skin of the equipment. So if you have metal clad or metal enclosed gear, you have transformers, you touch to the outside grounded, skin of the components with this, and you are looking at a decibel value on the display, and you're also looking at a thing called a phase resolved partial discharge plot, which you can get from this device or from this device in conjunction with an app on a smartphone, and it allows you to differentiate between background noise and actual partial discharge that's a result of something going on inside the equipment. So there are things in industrial environments, in utility environments, that can generate transient earth voltages induced in the skin of that equipment, but it shows up as noise, and through some algorithms in the software, you're able to differentiate between what's just background noise and what's an actual partial discharge event. So you would take a unit like this and you would go on multiple places on a piece of gear, all right, from all directions of the gear. And if you are sensing something that looks like PD, not noise, you would try to pinpoint, well, in what quadrant of the equipment is it? Where might it be, the strongest signal that I'm getting? Because the closer I get physically to the actual partial discharge event, the higher level of TEV I'm going to see in my capture, with the software and with this handheld device. So it's really good at doing the detection of this partial discharge within insulating materials. Now, this same unit also has a built-in ultrasound sensor. So ultrasound is above the range of human hearing, above 20 kilohertz. That's about where we cap out. So anything higher than that is classified as ultrasound. Now we're typically listening in the 40 kilohertz range, but it is a line of sight transducer, which means I have to have sort of a direct line of visibility for the sound waves to travel through air from the source of the defect to my sensor. So it can be difficult to do on equipment that's completely, hermetically sealed up. There's no air vents to listen into. There's no seams around the enclosure. So sometimes we look at also embedding ultrasound listening ports on equipment, or even ultrasound sensors on equipment that we can plug into, especially when it's completely outdoor rated, hermetically sealed equipment. So you're in this instance looking more for those airborne ultrasound signatures that come from the surface events, arcing, tracking, and corona. In severe instances, you could have cable insulation defects where the sound, it's gotten far enough along, and maybe it's even right near the surface of the insulator where it's managing to transmit out into air, and you could detect it with an airborne sensor as well. All right, but that may also mean that you're very close to a full-blown failure of the insulating material. So if you're picking up airborne that seems to be not arcing, tracking, or corona, but something else that's not fitting the normal waveforms of arcing, tracking, and corona, it could in fact be a cable insulation fault that's getting ready to let go. So we can see these anomalies in a few different ways. We see it just as a level, a decibel value, which is, the units we use for measuring the power of a sound wave. We use inside of the software that's running, the app that's running, that's coupled to the handheld device, we see these plots, which are partial phase resolved partial discharge plots. And I'll show a couple of examples of those a bit later. And we can also do some data trending. So we can go around to different assets and we can log them in a database and take measurements over a period of months or years, so we can see how things are trending. How are they changing? Are we seeing, higher levels of TEV, higher levels of airborne ultrasound on a particular asset now than we did 6 months ago, 12 months ago, which can be indicative that a fault is progressing, right? That a fault is actually getting worse, and we need to start thinking about what are we going to do as far as corrective action. Where do we apply these? Well, the electric utility industry has been relatively quick to adopt this type of technology, but we're also seeing a lot of adoption with this transient earth voltage and airborne ultrasound for anyone who owns their own medium and high voltage substation. So heavy industries, automotive, petrochem, steel mills, pulp and paper, etc., they are all kind of looking at this on their 5 kV and above equipment as another way to do condition-based maintenance and monitoring and assessment of equipment health. So it can be, done by an electrician or a mechanical, technician to go out there and do some assessments on your condition-based assets. You're keeping the equipment closed and guarded. It's all being done with the equipment, energized, but completely sealed up. So no need for any kind of special PPE. People are not going to be opening up panels in order to do this type of work. That's not what we want to have happening. So we have this Sonus PD unit. It's in a plastic housing. It's got an OLED display. It's got 2 types of sensors. It's got an airborne sensor for airborne ultrasound, but it's also got the transient earth voltage detection capacitively coupled sensor as well. Very small units, rechargeable built-in battery, long runtime, good IP rating on these units as well. You've got a touchpad, headphones, carrying case, all of the things that you need to really make a kit that will allow you to do this type of inspection on your assets. Now, you can also get for overhead distribution equipment. So if you have a substation where it's majority of the equipment is overhead structure, there is a parabolic dish attachment that you can get for these units as well to allow you to do airborne ultrasound on that infrastructure. You can also use these units for structure-borne ultrasound, although we don't think it's necessarily the best unit for that. It does functionally work as a structure-borne ultrasound as well. So you can do valve testing, you can do motor bearing, and all of the things that you can do with structure-borne, you can do with this unit too. It gets paired to an app on a smartphone. And then we can also have software for analyzing the waveforms that you might be capturing in the airborne with the airborne module, so that you can tell whether it's arcing, tracking, or corona by looking at the time and frequency domain of the waveform that you capture, that ultrasound waveform that you're capturing. So it's a very interesting and very versatile device. So it's easy to see if you've got airborne emissions or transient earth voltage present. It's an easy to see screen. It's a Bluetooth connectivity to an app, so it's super simple to use. It's very intuitive interface as well. So how do you know if this is the right thing for you? Well, have you ever had any failures that you think were partial discharge related? And as I mentioned, up to 80% of failures of medium and high voltage equipment start out as PD. They start out of this partial discharge, whether it's surface event or an internal event like the one that you're seeing here that started eating away at this insulator until boom, it no longer provided its insulating capability and it failed outright. How are you currently doing partial discharge testing, right? Are you doing any whatsoever? Well, so if you've got this device, you can actually, as I said, differentiate between background noise and true transient earth voltage. So it gets you to the point where you can do quick diagnosis of potential fault conditions within the equipment and then make some more intelligent maintenance decisions as to where to focus your corrective action efforts. What would happen at your facility if a partial discharge was to occur? Well, you might want to ask the guys at Delta Airlines, what does it cost when you have a piece of high voltage switchgear fail? They had a failure in December of 2017. That apparently the estimates were that it cost them about $50 million for the 11 hours that the facility there in Atlanta was down. So there were over 1,400 flights canceled as a result. So that's just the monetary implication. That probably doesn't include the reputational damage that they incurred as a result of that event. Now, how often are you inspecting your gear now? So with a lot of customers that we talk to, they are struggling because, they've inherited electrical infrastructure that is 50, 55, 60 years old sometimes. They've come into these older industrial facilities. They were built at a time, and at the time they were built, they were thinking probably 30 to 40 year, lifespan for this facility before a revamp. Well, we've stretched those lifespans. We are trying to, Band-Aid fix things. And, these types of problems, as I've said, they can manifest very slowly over time, but you may be getting to the point with your asset infrastructure that, it's been 40 years or 50 years of slow decay. These PD events taking place inside the insulation. Now is the time to understand, are there in fact components within my electrical infrastructure that are at high risk? So how does it work? Well, pretty simple unit. This is kind of a virtual demonstration. You take the unit out, there's a little test puck that has a press button that you can then have it generate both transient earth voltage signal and an airborne ultrasound. So you turn on the unit, you put it into transient earth voltage mode, you hold it to the tester this way, and it's going to give you a reading and saying, oh, it's 48 decibels, but it's mostly noise. It's saying this is 47 decibels of noise. So it's giving you an indication of the total level that it's seeing, but it's also saying, hey, this is just a noise signal. It's not real partial discharge, it's background noise. Well, it's background noise from our tester, but the tester is just proving that the unit is working. Right now, you can switch the unit hitting the mode key, the M key, into the airborne emissions mode. And then you hold it up to the actual airborne generator. So it's a little ultrasound generator that's part of that test unit as well. And it's going to give you an airborne emissions level of 48 decibels. So that's what it's hearing. Now, if you plugged in the headphones at this point, you can listen into that as well. All right, now go up to a piece of your equipment. Start using that TEV mode sensor in multiple areas on the equipment. Listen in if you're seeing anything. Look at the decibel value that you're getting. Look at the noise rejection level that you're getting, right? So you can just by that display tell whether or not you might have partial discharge taking place on a piece of equipment. Now, what you can also do to test it is you can hold that hockey puck tester up on the gear, a couple feet away, and you will see that as you get closer with the handheld sensor to that unit, it's going to read higher and higher levels of transient earth voltage. So it's sort of showing you, hey, when you have a transient earth voltage event that's going on, it's inducing voltages in the skin of my equipment. As I get closer to the source of it, I'm going to see higher and higher levels of decibels as a result of getting in close proximity to the source of the fault in the first place. Then you can go out and try it on some of your equipment without the tester and start looking if you're seeing unusual things going on there. So experiment with the unit, hold it up against panels, try different things, see what's happening, and just do what you can. Now, when you pair the unit with the app on the smartphone called the Sonus PD app, it's a Bluetooth pairing, and then we can start seeing these phase resolved partial discharge plots. So this is a PD plot with relatively low levels of noise and high levels of partial discharge being displayed. So that tells us we've actually got a defect that's going on somewhere in proximity to our test point. So we do have to be careful, as I mentioned, about noise. So we can have situations like this one on the right at the bottom where it's just a lot of noise. This could be a lighting ballast. This could be a few other things which will generate partial discharge noise and induce some transient earth voltage in the equipment in proximity. All right, we can also have high levels of noise, but also still see PD. inside the equipment. So just because there's noise doesn't mean that we won't be able to isolate out the fact that there's a partial discharge event in fact occurring inside the equipment. So don't let this noise thing worry you. We have algorithms embedded in the hardware and the software that kind of differentiate out the noise by looking at where these pickups are of the transient earth voltages, where are they happening in the voltage waveform of the equipment to which we're connected. And then, try it in airborne emissions mode. So listening in for those ultrasound signatures. And you can try it around the seams of equipment, on air vents to the equipment, or through a specialty, ultrasound port like the one that you're looking at here. And then, of course, if you do have overhead structures, we have the parabolic attachment. So you can use it for, again, listening for arcing, tracking, and primarily corona that you would hear on overhead, substation switchgear at your facility. So that's it for today. That's the Sonus PD in a nutshell. That's a quick overview of it. If you have more questions, if you need more information, please don't hesitate to contact us at www.iris.com, or you can call us at 941-907-9128. Thank you.